Hello, everybody. Today I'll be giving a small introduction to computing science or computer science, or to what some people will simply call software development or coding. So, the objective today is to give a broad overview of what computing science is, as well as some of the applications, and we'll work on defining a few terms and then lay the groundwork, if you wish, for some future classes. So stay with me and we'll see where we get to today. So, first thing I want to point out is that there are computers everywhere and they've been with us for many, many years, for hundreds of years. For example, clocks compute time. There are many different computers, all of them compute different things. And clocks, they compute time. Stonehenge, for example, the Incas, Egypt, China, we've had some of these type of computers for thousands of years. So when somebody says that, oh, computer science is a new field, it's very true. It is a new field, but it has a long history, and sometimes when we just learn about coding and writing code, we forget that some of this old history, some of this long history that computing has and how it matters. This is how we came to be where we are today. So first we'll go through a quick list of some of the more interesting or varied pieces of computing machinery over time. And there's no way that I'm doing justice to any of this. But I will attempt to give a flavor if you wish. So this one is an abacus. This is something that many of you likely already know about or have played with in grade 1 or grade 2. It was invented somewhere between 3 and 500 BC, and there's many different types. This is just one type of abacus. It's a fairly commonly seen one if you see one today. Another one, for example, is a slide rule. This was invented by William Outright. I hope I got that right, in 1622. And people were taught how to use this implement in schools well into the 1980s. Today, it's been replaced by basically modern scientific calculators, or pretty much any scientific calculator today will do everything more and faster than what the slide rule did for the most part. Mechanical calculators. So the slide rule you can look at and say it's a form of mechanical calculator. You move things back and forth in order to input questions and get out answers. Well, mechanical calculators really started in the late 1600s, and they were developed into many, many different types of things throughout the 1700s and 1900s, 1800s, 1900s. For example, cash registers were used well into the 1900s, and many of these were mechanical cash registers. You would punch buttons and, little levers and rotating things would calculate and total things up. A difference engine, which was designed many years ago, even before mechanical calculators and mechanical computers really became to be, by somebody called Charles Babbage. The first one of these was built and completed 153 years after it was designed. Funny enough, the original design, just modernized slightly for at the time current production practices, actually worked as designed. From there, we see other types of mechanical computers. This is a Curta from 1948. And this is a single-handed mechanical calculator that could do a number of different things. You're welcome to, search for this on Google, and you'll find Wikipedia entries and other things like that, which talks into much more detail over what this particular calculator could do. From there, we move into the realm of, we skip past the electromechanical computers, if you wish, where electricity was used to actuate relays used for switches. And there were some computers built that way, but they were not very common. Some calculators, I guess I should say, were built that way. The first one that was, in some sense, all electronic without needing extra mechanical switches to do any of the calculating was called Colossus, and it was the beginning of the era of vacuum tube computers. And these were significantly faster than mechanical computers because you didn't have to mechanically switch current or electricity through different circuits. A vacuum tube could do this much faster. And because there wasn't mechanical wear and tear on things, they were much more reliable than their mechanical counterparts. Naturally, these computers were significantly less reliable than today's computers, for example. From there, we went on to bigger and better vacuum tube powered computers. This one is called ENIAC. This one consisted in its heyday of some 20,000 vacuum tubes. It consumed 18,000 square feet of space. This is the size of a decent sized 3 or 4 bedroom house. And it would consume 150 kilowatts of electricity. It is said when they turned this computer on, the lights in the city where this was located would all dim because of the amount of electricity that this one computer would consume. So if we look at this as the previous, if you wish, set of computers you have, or computing devices, and we move past vacuum tube computers into transistor-based computers, we have a very rich history from the beginning of when a transistor was first used, from the beginning of the first microchip up until today. And a full 6-month, 8-month computer class of the history of computers could likely be made to discover and talk about all the different ways that these new computers, if you wish, became to be, and all of the advances that they all brought to the table. For the most part, we're not too worried about how the actual implementation, the physical implementation of all of these computing devices came to be, and what the physical properties of all of these transistors were. That can be an interesting study in itself. And for anyone who's interested in learning about how to physically build computers, both in terms of a historic context, and in a current and future context, that is a field of computing science or computer engineering, electronics engineering, electrical engineering that I don't possess, and that I can't really do justice in. I would encourage you, if this is what you wish to know more about, to seek out I believe there are some YouTube channels that will at least give an overview. And beyond that, there might be some books or some university or college classes that could help out with it. But this is a domain that I do not know as much about. So this is about as much as I will say about that. Anyways, needless to say, modern computers have a relatively short history. There are hundreds or maybe even thousands of different types of computers that have been built. And when you move into the modern era, so like today, the computers are so complex that it is completely impractical to learn everything about them in a short course. And even a full university degree will likely only scratch the surface of what is contained within, and how a modern computer is built from the very ground up until it is completed. So to help us with this and not have to learn all those things from basic principles onward, is that we'll use an abstraction. And this abstraction will help us to simplify today's computers and help us to understand them. So this is the abstraction that we use for the most part when we talk about modern computers. Now, it may be a bit more involved, a bit more nuanced here and there, but in broad strokes, this is a diagram that largely encompasses what a modern computer, a modern computing device, digital computing device looks like. You've got some input on the left there, some input devices if you wish. You've got some output devices on the right, And you've got a CPU, or a computing central processing unit, in the middle. And you've got some memory, which is indicated by the box on the top there, to store temporary results and so on. And then you've got some storage at the bottom, indicated by the drum-looking thing at the bottom, to store things for more long-term use, uh, possibly for very long-term retention. So if we look through and we look into each one of these boxes a little bit closer, what we'll come into is some examples, if you wish. So these are some examples of input devices: a keyboard, a mouse, a trackpad. These all take input from your hands, and they're mechanical input devices that the computer can read and understand. A microphone is an input device where you speak or sing, where you have an audio that the computer is able to listen to and record. A game controller, a webcam, where you have a computer be able to get input video and process that video. There are many other types of input devices here. Some of them are switches, some of them are, sensors. For example, in your car, sensors that, sense when a crash has happened, or a temperature sensor, for example, to control how hot your oven is getting. All of these things that a computer gets as input, where it gets some data from the outside world into the computer, would be considered an input device. And then we have a set of output devices. And this is sort of the opposite of the input devices. It's where the computer ends up giving something to the outside world. So the outside world can do something with this, can see what the computer would like it to do. So a speaker, for example, is an output device. A computer can play some audio and some songs, and then through the speaker, it can put that song, that data that it has about the song, out into the world, and we as humans can then listen to it. A monitor is an output device where we can use our eyes to see what the computer is trying to tell us, what the program inside the computer is trying to tell us. A set of headphones, a plotter, a projector, a printer. A 3D printer is common today. Trying to think of what else. All of the motors that control a 3D printer, for example. If you've got a drone, the motors that control the propellers, for example, are also output devices that a computer can control and have some effect, have some result happen in the real world. Here are a set of storage devices. Now, a lot of these storage devices don't really exist anymore today. So, for some of you, this will be foreign territory, or maybe, long forgotten history. I know for myself, I have not used a floppy disk in many years, likely over 10 years since I've last used a floppy disk. But to give an example, a flash disk, a floppy disk, a zip disk, a CD-ROM, a DVD-ROM, a disk drive, it's also commonly called, or maybe storage tape for backup and other purposes like that. Another common one might be, some online storage site or some cloud storage. And these all can be looked at as longer term storage. Now, by longer term, it may just be for minutes or hours, but in computer times, those are considered long term, right? If you turn your computer off and then turn it back on, the information you stored on these devices is still there. So it is retained for a longer amount of time. And then the second last piece, is considered memory. And the picture that is shown here is some SD-RAM, happens to be SODIMM, which is the memory that used to be put into a laptop when you could still put memory chips yourself, memory cards, into your laptop yourself. Today, most laptops, the chips that you see on this particular card, the little black rectangles there, they are permanently attached inside the computer, inside the laptop that you have. So that makes it more reliable. It also means that you can't change the amount of memory that your laptop has anymore. Used to be very common to be able to do that, even 10 years ago. And there's many different types of memory technology that has existed over the years, right? From magnetic core memory, where there was literally a little magnetic donut that would store each little bit of information, to something called static RAM and then dynamic RAM, and today it's usually called SD-RAM, or maybe just memory. Um, it's less important exactly what technology we use today. Uh, you know, Certain types of computer users might care a lot about the speed and the latency of their memory because they're doing high performance computing or they're doing gaming or other things like that. But for the most part, for our use, it is enough to know that there is memory in the computer, and it is short term storage where if you store something in memory and then turn your computer off and then turn it back on, what you had stored in memory is now gone. So it is short term. It is really only there during the amount of time that the computer is on and actively using that memory. And then lastly, we have the CPU, the processing unit, the central brain, if you wish, of the computer. And over the years, there have been many vendors, many different companies that created these. Today, there are less of them, through consolidation and some of them going out of business and so on. But for the most part, there are two large vendors for home computers, if you wish. And then there is a consortium of other vendors together. So the two large vendors are really Intel and AMD. And you might hear of like an Intel i9 processor or an AMD Ryzen processor. And then the last one is sort of a consortium of different vendors, if you wish. It's called ARM. So you might hear this in terms of Chromebooks and other computers like that. Usually these are just a single chip, and what you see the person holding in their hands there is one of those chips. Contained within one of these chips is billions of transistors. So before we were talking about 20,000 vacuum tubes in something the size of a house. So if you want to think of a vacuum tube as a single switch, a single transistor, there was 20,000 of them in something the size of a medium to large house. Whereas today, something that fits in your hands on the chip itself is actually tiny. It fits on the tip of your finger. So something the size of the tip of your finger has billions of transistors. It has billions of those switches. So literally millions of times more. Not just a million more, but million times more. It's like having a million of those houses, a large city of those houses, all on the tip of your finger. And that is what today's CPUs, or central processing units, consist of. And then you have all these pieces. You've got your CPU, you've got your input devices, your output devices, your memory, your storage devices. And they all sort of need to be held together by some glue if you want. And that glue is called a motherboard. And here is an example of a motherboard. This is a few years old, but today's motherboards may look a little different, but generally they look, they have the same function, is what it comes down to. And if I quickly describe this particular motherboard, you've got the square-looking white piece in roughly the center, maybe slightly to the left of center in this particular board. And that's where the CPU, the central processing unit, plugs into. And then if you look straight up from that, there is a set of blue sticky row looking things, and that's where the memory would plug into. And then if you look below the CPU socket, that was the white square thing, below that you see some pink connector, and if you look a little bit to the right of that, you see some other pluggable places, connectors, and that's where the input and output devices would get connected. The audio, for example, there's a blue, green, and pink connector. That's where the audio would get connected. And then you see some USB ports. That's where a flash drive, for example, would get connected. So that would be a storage device. And the monitor and keyboard and other things like that would get connected there as well. And then if you look to the very right of this particular motherboard, you see some white slots, and what is commonly put into those slots, there's also a black slot just before that, but I digress. What is put into those slots is largely storage and other input-output devices that need a faster connection. So a graphics card, for example, or a storage card, a networking card, for example, also. So this is the glue that holds things together. And that's basically where we come to when we're talking about an introduction to computing science, to computers. There's not a whole lot to it at the very bottom. We can abstract, we can make things be simple boxes so that we can talk about them simply and then build on from there. Now, granted, how each one of these boxes is built can be very complex and can be very involved, and there are many people that enjoy building each one of these individual pieces. There are people that enjoy building their own keyboard, and it can be an awesome thing to learn how to build your own keyboard, make it be exactly the way you want. Or there are people that learn how to build central processing units. Now, they're likely not going to build their own chip, but they might use a programmable chip to build their own little processing unit. And all of these boxes, if you wish, that I've talked about before, have got enthusiasts and researchers, many different people building new ones of these, building old ones of these, rebuilding old ones. There's a large world there, if you wish to explore the hardware side of this endeavor. So, as part of an expansion, if you wish, oh wow, my brain just went sideways there. I apologize. But as part of just easy reading, if you wish, and enjoyable reading, I find. I've put down 3 books here. If you're wanting to know some of the folklore, some of the history, some of the stories behind our technology, behind the world that we have come to live in, these are some of the books that I have enjoyed immensely. So the first one is Soul of a New Machine by Tracy Kidder. This is a book which talks about the creation of a new machine, a new mini supercomputer at its time, and it is a very enjoyable read. It is a read that is approachable and understandable by somebody that does not know the inner workings of a computer. So on that level, it is enjoyable. The next one is The Cuckoo's Egg by Clifford Stoll. If you're into hackers and hacker culture, then this is an interesting read about an actual event that happened where Clifford Stoll actually discovered and tracked a hacker that was within his system. And it is one of the, if you wish, early accounts of how this came to be. And this is written again from the point of view of somebody that did not know and understand computers to the level that the hacker did, but had to become familiar with how these things were done, how the hackers operated. And he wrote a very interesting and compelling, if you wish, almost drama that is a fairly easy read, even for people that do not understand all of the ins and outs. And the last one is a popular movie, I believe, is the original book. Um, I thoroughly enjoyed the book, and I really do encourage you to read some of the history of NASA and how some of the culture and people, how their lives were while they were working at NASA during a time when the humans went to the moon, when during a time when NASA was doing very huge and grandiose, if you wish, almost projects. So I encourage you to look for these three books, any one of these books, quite frankly, and enjoy some analog time where you're just enjoying reading this one of these books or all of these books, and it gives you an insight into different aspects of the world that we live in with respect to technology today. And then there is a small bit of homework. So ultimately, in this set of classes, I want you all to get hands-on experience working with computers. So we will work through a set of computing science concepts as time goes on. But in order to do that, you will need some tools, and you will need to be able to use these tools and learn how to use these tools. So the first homework is basically fairly straightforward. It's get your environment and your computers and your tools set up so that you can actually work through with me on these upcoming classes. So number one is to obtain your tools, your laptop, desktop, computer for you to learn on. Doesn't have to be very powerful, but it should be powerful enough to run Go. So modern enough, let's say within 5 years old or so. And there's a link in the slides right there where you can see more specifically what the requirements are. And then the second one is to attend the first lab. So here I've called it Lab 01, Environment Setup. And that's me running through setting up this environment that we're going to be using. So it'll help you set your programming environment set up. Now the lab is Mac specific, but it should give, if you're not working on a Mac, if you're working on a Windows machine or possibly even a Linux machine, it should at least give you an overview of similar steps that you would need to do on a Windows machine. In this case, unfortunately, Google is a friend. So if you get stuck, Google what you would ask somebody, and hopefully, the first couple of links will help you be able to look through something. Reach out to a techie friend, right? If you know that somebody who's working in the computer industry and programming or whatever, they can likely help you run through this first setup. If you're, a parent and you have some children that are doing things like this, by all means, have them teach you something, right? Now, there's really two reasons why, and I try not to get into too much here, but there's really sort of two reasons why I chose Go. Let's say three reasons. One is I actually enjoy programming in Go, so unfortunately, that means that I'm going to be biased towards it. Number two is it's a fairly straightforward language to pick up, and it allows you to go a long way. So it's sophisticated enough for us to be able to use it to learn all the concepts we need to. And lastly, the people who work on Go, the um, the community, the Go community, I have found to be very receptive to new people, to newcomers. So the people who work with Go or work on Go, we call them Gophers, and Gophers are friendly and helpful. I've not met an unfriendly Gopher yet. So reaching out to the Gopher community or a meetup group to help you with setup of your environment, you will more likely find somebody that is willing to help you out in these early days. And that can mean all the difference between making this an enjoyable experience for you or one that is very, very frustrating in the beginning and hard to get over. So if you are in the segment, if you are part of the group of people that does not have easy access to people who can help, and where my lab does not help you a whole lot, I apologize up front. It is unfortunate to have to feel frustrated or lost this early on, but I encourage you to reach out and try. Watch some extra YouTube videos or watch some extra Vimeo videos. Pull down another tutorial or two and run through it step by step. And I promise you, you will get over that initial frustration and feeling of lost. And hopefully watching my lab instructions will give you an idea of how far along on some of those instructions you need to get in order to be able to join us in our next classes and our next labs and follow along in whatever your environment is. So I wish you luck. Best of luck with the homework, and I'll see you again, or you might see me again, I guess is the best way to put it, soon in the next video.